We are in Chapter 3, Implicit Differentiation. We're going to talk about yet another way to take derivatives. All of the same rules still apply. Derivative of sine is going to remain cosine. The derivative of x squared is going still to be 2x and so on. But now we're going to incorporate chain rule, and we are going to take derivatives of expressions that are not functions necessarily. Now, why would we need that? Please remember that the main point of differentiation is figuring out tangent line, which measures the slope, which means that we have to be able to find the slope through derivative. And once we have the slope and the point, we can find the equation of the line, which is the tangent line, which measures what we want to measure. And now let's say you have a function, and then you pick point. Well, clearly you differentiate. There is a tangent line. We're all good to go. And you should be able to calculate this fairly quickly. So the point is at a f of a. The function is f of x. The tangent line is the TL. And you should be able to solve this. Now, the function could be trigonometric, exponential. It doesn't matter what it is, as long as you are able to differentiate that and compute the point at it to find the slope, you're good to go. The key point is that you have the function which you are differentiating. Now, what happens if a relationship that you get is not a function? Circle, not a function. It has x squared plus y squared is equal to, let's say, 9, if the radius is 3. That fails vertical line test, therefore, not the function. But I can still draw tangent lines all over the place, which means that the derivative of this thing still exists. And it can be found, and as a consequence, we are still able to compute the tangent line. So even when the relationship given is not a function, we can still perform the same calculation. So that means that there has to be a way to find the derivative of expressions which are not functions. We know how to deal with functions. That's what we did so far, including the product rule, chain rule, quotient rule, and then basic derivatives, putting all of that together, making it as annoying as possible. All of that belongs on the left. And now for the right side, where we're going to replicate everything we did so far, except we will be taking the derivative of x and the derivative of y. So now, the first thing that we need to talk about is the notion of the explicit and implicit function, so you know which methods you are using in which case. So explicit function is when you are able to write y equal f of x, which means you are able to isolate y alone on the left. So I'm just going to put able to isolate y on the left. So that will be explicit function. Now we're going to have the implicit, and I'm going to call it relation, because it could be a function, but it doesn't have to be. So implicit will be when you cannot isolate y, so we would write it as some kind of f of x, y, and equal to 0, because we really cannot separate. So I'm just going to write over here, cannot separate y's from x's in a fashion before. Immediately example for this. Let's say you have y cubed minus y is equal to x plus 3. Even though you have all y's on one side, it is not y equals everything else. And there is no way for you to write this as y equals everything else. You can write it as x equals everything else. We can fix that as well and put plus 3 sine x, and then you're doomed. But there's no way that you can write this as y equals everything else. And this would be known as the implicit formula. You can still calculate stuff. Give me x, I'll find y's. Give me y, I'll find x's. That's not a problem. Computation is not a problem, and if you are hicking up, if you have a hiccup on figuring out how to compute any of these things, fire up Mathematica, plug in values, it's done. But there is no algebraic way to put this to be y equals everything else, so that is implicit. It still can be graphed, and because it can be graphed, that means that this particular thing has the tangent lines all over the place. I need to be able to take derivative of expression like that. So that's the first piece of the puzzle that we have to understand. So far in this course, we dealt exclusively with explicit forms, functions, and we didn't bother defining them or anything because they all looked alike. Y equals f of x. That f of x is going to be a whole mushmash of things, whether it's trig, exponential, all of them mixed, whatever. Now we are going to have a situation like this. The second part of this is to realize that y is equal to f of x, which means that dy dx is that y prime or f prime of x, whatever you want to call it. I'm going to put this like using the red and say derivative in terms, or sorry, in respect to x. So derivative in respect to x. Now, every time when I want to take the derivative of y, I have to treat that y as a function, which means that I have to add the derivative to it as a chain rule. Not add, multiply. So say that y is equal to, I don't know, 3x squared minus 5. And you are taking the derivative of the entire expression denoted this way. Well, when you apply the derivative to y, all you get is dy dx, right? Because the y will multiply dy dx, and we'll fix that later. And on the other side, we are getting 6x, and then minus 5 is just 0. So we know what the derivative of y is. Now on the side over here, I want to take the derivative of y squared knowing what y is, which is 3x squared minus 5. I hope you guys see a chain rule there. I can plug in 3x squared minus 5 and then FOIL it and do all of that. But why would we? I can just take the derivative of y as 2y and multiply that as a chain rule, which is the derivative of y, and we know that's a 6x. So the derivative, when you are taking derivatives of y's, they will behave the same as if you were taking derivative of x's. And then you will multiply the chain rule piece, which is just times dy dx. Now, if you know what dy dx is, you just plug it in. So now what does that mean? That means, what was our previous function? Was y cubed minus y equals to x plus 3, I believe. We can take the derivative of this simply by denoting, all right, I'm taking the derivative in respect to x, and observe that the whole expression, the entire expression is in these brackets because I am taking the derivative of every single term. The rule from derivatives, which says that you can take derivatives term by term, still holds. which means that you will be taking 4 separate derivatives there, preserving the signs as they are, including equal. So what would be the derivative of y cubed? 3y squared. Now, we have to multiply that by the chain rule piece, dy dx, because we were taking the derivative of y in respect to x. The variables don't match. Therefore, we are following with a chain because, I'll just write here, remember, I'm so confused now. I said word remember 50 times in my head because I know I misspelled it. This is one of those foreigner hiccup things when you get hanged on a word and you just freeze. And I'm gonna try it again. Get the points? There we go. Awesome. Remember that y is f of x, right? So y is some kind of function. And then if you take the derivative of it, you are going to get derivative on the other side. So I'm taking the derivative of y, and because y is a function, I still have to follow it by chain. What is minus? What is the derivative of y? 1. So 1 times dy dx. What is the derivative of x? And what's the derivative of plus 3? 0. I'm going to write it here just because I'm awesome. So you hopefully see one-to-one correspondence between the terms and the derivative. So each term had the derivative performed on it. And now we have this new expression. Now we want to know what the derivative is. Well, hopefully we just quickly factor out dy dx. In parentheses, we are going to get 3y squared minus 1 is equal to 1. And to get dy dx alone, we simply divide by 3y squared minus 1. And ta-da! That would be our derivative. So now if I have x and y, I can compute the value of the derivative, which gives a slope, and then further we can find the tangent line. Yes?
When you're writing dy dx with 3y squared minus 1 times dy dx and all that, what derivative are you referring to?
What is what?
When you write 3y squared dy dx minus, that, what derivative are you referring to?
Well, derivative of this is there,
Right.
and then this is the chain because of the chain rule. Derivative of y is 1, and then this is the chain rule because we are taking the derivative of y in respect to x. And that is something that I actually have to explain now a little bit more, so hopefully it will be clearer when I'm done with this next showpiece. We are getting now into this picky situation that we did not discuss earlier, and that is that we are taking the derivative in respect to x, or in respect to t, or in respect to y, or anything else. And for that example, for us to understand that, I will also discuss a little bit the notation and why I don't like y prime as notation at all, and I try to avoid it almost all the time. So I will start first by saying that y equals, let's go with ax squared plus bx plus c. This is the standard form for our quadratic function. And now we're going to write few derivatives. And I'm going to use the dreaded y prime notation. So I'm going to write a few things, and then you guys tell me what you think. So we clearly see here that notation is telling us that the function y is f of x is given as the ax squared plus bx plus c, and then we see 4 different rows below, each one claiming to be the first derivative of that expression. Right? Is that correct? Is any of those correct? Are some correct? Are all correct? What do you think? Going back and thinking about the story of parameters and story of variables that I gave at one point. What do you think? The first one looks right. Why would that be right? Okay, exponent to the front, so that's 2 in front. Good.
X is 1, so it's left with b, and then the constant is 0.
Excellent. That's perfect. So as you're taking the first derivative here, that's a coefficient gets rewritten. The derivative of x squared is 2x, so here's 2x. The derivative of x is 1, so 1 times b is b. We call it is b because it's multiplied. And then c is the constant derivative of any number. Any constant is 0. So that appears to be the first derivative, and that's good. Now how about the x squared? Would that be a derivative? So this is where we one more time get into the issue of variable versus the parameter. And then also we're talking about the notation for derivatives. And also learning something crucial for implicit differentiation and lectures to come. So I will start by saying that all of these are correct. But just notation is awful, so nothing makes sense. So I'm going to use superior notation, which is that f of x is equal to ax squared plus bx plus c. And then over here I will say that dy dx is equal to 2ax plus b. And in order to make the second one correct, I have to say dy dA is equal to x squared. At which point this becomes correct. By saying dy dA, I am actually spelling out that the derivative was taken in respect to a, which means that the a becomes the main variable for the problem. And everything else becomes either a constant or a parameter. That means, if you see dy dA, that means that x is no longer a variable. And any term that does not contain that variable is going to be a term that it's a constant term. So now, if you are looking carefully at your function, if you are taking the derivative in respect to a, then derivative of a is 1, just like derivative of x is 1, right? Are we all cool on that? If you understand this, the rest of this chapter is going to go very easy. So the derivative in respect to a, or in respect to x, or in respect to b, or in respect to c. So now, why everything else dies? Well, observe that the bx term does not contain a, which if we are taking derivative in respect to a becomes a variable. No variables there, which means it's a constant term, so it dies, it's 0. And same goes for term c. So it's x squared plus 0, just x squared. And now you just fill the rest. dy db, which is just x. So the first and the third term do not contain b, and therefore they are zeros. And then the last one is dy dc, and the derivative of c in respect to c is 1. Yes?
So I get why, like dy dA, everything else goes away, but if if that's supposed to be the derivative, why wouldn't it be 2x, and why wouldn't that x be a? Why are you writing this x?
But a is the variable there. X is the parameter. Because the denominator of this superior notation, this is Leibniz notation, denominator there tells us what is the variable, which means that all other letters in that expression in calculus 1 become parameters. So x is no longer a variable, and we have to actually walk away from that notion for calculus course because other ones are coming up, like t for time, and other things later on, calc 2, calc 3. So we are walking away from this idea that only x can be a variable. And we are bringing in the notion that any letter can be a variable. And that is something that we need to address. So if I have, let's say y is equal to 3km squared minus vm plus 9, something like this. To practice, I can ask you, what is dy dk? What happened? 3m squared. Very good. 3m squared. Because the derivative of k in respect to k is 1. Just like the derivative of x in respect to x is 1. So now, the derivative of that term, k would be 1. And then you have 3m squared. No k terms. No k's in second and third term. So they're both constants. They go to 0. Now, as the contrast, what is the derivative dy dm? Yes. 6km minus v. Very good. So now, since m is the variable, the derivative of that one is 2m. 2m times 3k is 6km. Over here, the derivative of m is 1. So minus v, no m's in the last term, so plus 0. Are you on green on this? And we can also ask what is the derivative in respect to v. Anyone? Negative m. So we have the 3 separate derivative calculations here. And as you can see, all of these first derivatives are different because we are doing the differentiation in terms of a different variable. Now this is going to come in very handy in chapter in 3.11, my favorite, related rates, because you will be relating two concepts through mathematical equations that contain derivatives, and you will, I don't think you're going to see x and y in that section at all, because we have time and we have other things that we want to compute. So there's all that stuff. So that was a little bit on notation and on the idea of these variables. Now I want to also discuss one more thing. We all know the formula nx to the n minus 1, so what's the derivative of x? So if you are taking the derivative of x in respect to x, you would just put 1. Why? Well, you say the formula is nx n to the minus 1, If I just have x, then that's x to the 1. So it's 1 times x to the 1 minus 1, which is just 1 because x to the 0 is 1. And that's using the formula, sure. But there is something cuter that we can do. And that is just to realize that this operator is multiplying. Because the word of in mathematics means multiplication. When you're asking for 30% of something, 30% of, I don't know, x means 0.3 times x. So the word of in mathematics does translate as multiplication. So if you are looking for the derivative in respect to x of x, that means that you are multiplying these two fractions, which means you are getting dx over dx, and that's when it cancels, it's 1. If you are taking the derivative of 10x, then you are going to have 10. Why? Again, if you are to multiply using the simplest algebra, you will have 10 dx divided by dx. These guys cancel, and you get the 10. The same way. So that's something that we also should know. Now let's look at the circle. X squared plus y squared is equal to r squared. This is centered at origin. Centered at origin, which has coordinates 0, 0. So I asked earlier, what's happening with x squared plus y squared is equal to 9? Well, let's differentiate the entire problem in respect to x and see what happens. What is the derivative of x squared? 2x. Now, technically, I could follow this with a chain, dx over dx, but I don't have to. I'll come back to that later. Plus, what's the derivative of y squared? Times dy dx. Very good. Equal to what? 0. So now you just solve this for dy dx. So 2y dy dx is equal to negative 2x. Divide both sides by 2y. Dy dx stays as negative 2x over 2y. These guys drop. And then I have my derivative for the circle. And the derivative for the circle is dy dx is equal to negative x over y. So now I am able to compute any tangent line along the circumference of a circle. Yes?
I think you said this before, but when we see 2y next to dy over dx like that, we're assuming that it's 2y multiplied by dy over dx.
Yes.
We use the division basically.
Yes, this is multiplied. Therefore, you will use division to peel off the 2y. So divide both sides by 2y. Great. So let's find the tangent line somewhere. So say we have the formula. Find tangent line at, and let's compute the value. So if x is, I don't know, x is 2. So compute the tangent line for x is equal to 2. Now, in order for you to compute the tangent line for x equals to 2, you have to find the y value, because once we have x and a y, we can plug those in there to get the slope, and then we can use that point that we've just found along with the slope of the tangent line to find the actual tangent line, equation of the tangent line. So now what can I do here? Well, I plug 2 into the formula. I get, well, let's write one more time. So 2 squared plus y squared is 9. So y squared is equal to 5. And here is the $1 million thing. Don't forget to write plus minus square root of 5. You see that we are actually getting two values there? Anyone? We're getting positive and negative because we had to take the square root of both sides. So now we actually have 2 points to worry about. Tangent line at x is 2 and y is root 5. And x is 2 and then negative root 5. So those are the 2 points to pay attention to. And that's where we find the tangent lines. By the way, this was all arbitrary. I picked an arbitrary 2, so I don't know how the calculations are going to end up, but let's power through and see. So what do I know so far? I know this derivative, and I know that I need to compute that derivative at our newly established point. So slope m is dy dx computed at 2 root 5. And that is, so, yep. All right, so we have the values. So we know that the derivative is negative x over y. So that's going to be negative 2 over square root of 5. And then we rationalize because we should. Or maybe we can rationalize later. Let's rationalize later if we end up, because we still have other stuff to do. And then we have 2 root 5 as a point. So they will meet at 2 root 5. And the equation of the line, the tangent line, should always maintain its slope forever, obviously. That doesn't move. So what do we have? We have y equal mx plus b. Y is root 5. M is, oh, I never computed the derivative. No, I did. Minus 2 over root 5. Minus 2 over root 5 times x is 2 plus b, and somewhere I computed b. Where did I compute b? Oh no, we are looking for b. Wow. Wow. So root 5, and this is where the rationalizing kicks in, because you see root 5 in the denominator. So you have negative 4 over root 5, and you know what? I'm going to hit it with root 5 now because I can. So root 5 is equal to negative 4 root 5 over 5 plus b, and finally b is equal to root 5 minus 4 root 5 divided by, right, 5. So now you can combine these. If you can get the decimal value, no one technically cares. So now what's the tangent line? And it's very important to stress that that's tangent line at x equals 2. So the tangent line is going to be y equal m, which in our case is somewhere here. Negative 2 over root 5, thank you. X, and then we have plus b, which is root 5 minus 4 root 5 over 5. And as you can see, it's a messy answer, but we got it.
So would we have two slopes because we have the plus and minus?
Nice. Why?
Because the other one would be just positive slope.
Why?
Because you take the square root of both sides, you get the plus minus.
No, that's true for calculation. I'm asking physically why. You are 100% correct. So, yes, it's true it's circle because we have the circle formula. We started for there. So what's the issue? Why do we have two plus and minus? Yes, it is. Very good. The plus line is going to go like this, and the minus line is going to go like that. They are completely opposite. Come on. Projector is kicking up. There we go. So this is your positive slope, and this is your negative slope. They are completely different lines. So why do we have plus and minus there? Other than we must, because we took a square root. Memorize that. So now this is going to be one of those times when you guys get to be split into two categories. A category of students that is actually trying to understand this because you are trying to, I'm trying to hint that it's going to be extremely useful when you start doing whatever you're doing, but then I have to wait until 311 is done and some more sections for that to be really there. Why at x equals to 2 we have two values for the slope? Yes? Yes, thank you. Awesome. Number 1, number 2, number 3 for radius. Number 2 extends there, number 2 extends there. There's a tangent line that way, there's a tangent line this way. There it is. So, the number 2 is right here. And that number 2 gives rise to two y values, which breaks the definition of a function, hence the circle is not a function. It fails vertical line. But because that x gives rise to two different y values, each one of those is a separate different point, and each one of those has its own tangent line, and there's your positive, sorry, that's a negative, there's a positive, right? So we found this one, and as you can see, slope is negative going down. Now this line over here is going to be completely different. It's going to have the same slope, but it's going to be 2 over positive root 5. But this is going to be different because this y-intercept is when you extend this line this way, it's going to intersect there, and that point is the whatever decimal this gives us. This line will have this intersection point here, which would be a decimal from a different perspective. So every point on the circumference of a circle or any other function or non-function will have its own tangent line there, which has to be computed from scratch as soon as you move this point. Because this point, when you move this point, it moves the y value. When you move the y value, it moves the entire calculation for the tangent line. Yes? Yes. Not yet, but yes. We are going to intersect, in this case, at the x-axis. I'll get an application. So on. Measure the rate of change from all directions. So you might want to see accelerate and certain things like that. So there's a lot of stuff. Apart from that, creating a cool math problem for you to scratch your head on. It's like, how do I find this? Which is technical algebra 1, once you're done with all the calculus. So, to recap, and then we're going to do a whole bunch of these implicit problems. To recap, there's a lot of lag today. I know they did a system upgrade. So, yeah, we have to be a little bit patient with this now. So what I have here is implicit and explicit formulas and functions, and we are dealing with implicit differentiation this time around. The cheapest, lamest way, yes, I said it, to memorize this is to say take derivatives of y as if it was x, and then just right after it dy dx every time. That's the cheapest way you can think about it. The mechanics of solving the rest of the problem are the same in sense that you are remembering just what the basic derivatives are. And we can use it to find the most important problem, which is tangent line. So now what we are going to do is to solve a whole bunch of these implicit problems, see how they work. So let's start with problem number 10. So you try it, and then I will do it. Square root of x minus 2 square root of y is equal to 0. Wow. Come on, leg.
Is this free in the top right corner? I don't know if you hit the right.
Freeze, huh? Oh, maybe we should increase the temperature of the...
Maybe it's on the projector.
I'm going to actually stop I stopped the projection over there, and then I can always restart the projector. So it appears that it's not the software, it is something that the projector is. So let's reboot the projector then. I'm going to chisel these 2-3 problems on the board so you guys can projector. Because projector has to cool down first, and then I have to restart it, and it has to so here it is. Square root of x minus 2 square root of y is equal to 0. That's the first problem that you should work on. And then the second problem, you're going to love it. It says tangent xy is equal to x plus y. So these are the two. No pressure, you have 17 seconds. Questions? No, not yet. Eventually. Let's see if the projector is. There's still lag, but it's not as bad as it was. So the first problem, we are taking the derivative of x in respect to x. So what do I write? One half x to the negative 1/2, good, minus 2 times 1/2 y to the negative 1/2 dy dx equals 0. Now these guys cancel. So I have 1 over 2 root x minus 1 over root y dy dx equals 0. And now from this point on is algebra. You have to fish out dy dx. Use whatever witchcraft you know. It doesn't matter. Just get dy dx alone. So what do we have? We're going to have 1 over square root of y dy dx equal 1 over 2 root x. Multiply both sides by root y to get rid of the fraction, and then dy dx stays alone, and we get square root of y over 2 square root of x. Now you can go be cute and rationalize and do all the other things, but in a nutshell, we're done.
You have to rationalize.
Well, some people would say yes, and some people will say no. The reason why I say no in this particular case is because we don't know the value for x. It could be 4 or 16, where some will argue, but it could be 3. Yeah, but give me first, all right? Now, if this problem worked out to be, let's say, 15x over root 3y, then hell yes, then you rationalize definitely, right? Because root 3 is something that should not be in denominator at any point in time. So, as I said, our result, you don't have to worry about it because we don't know, we don't have the value for x. So leave it. Where if it was like root 3, then yes. Yes? The answer is probably yes. I'll take a look at that. I can't hear the air conditioning. You gotta get the volume up. Well, I can rationalize it now, sure. That's not a problem. We can rationalize it. If I'm setting this equal to 0, 0 is going to kill the denominator anyway, so it's going to be square root of y, right? Square root of y equals 0, so the only one is 0 in this particular case. So every time you can do the analysis and check. So you're saying that we should... no, you're still going to be stuck with the square root. Because if you square these, you're going to get the middle term, which will contain square roots. So yeah, this problem is what it is. Now, how's the tangent going? I'm sorry?
You start by subtracting tangent x, y, and z.
Nope. Don't need to. Just take the derivative term by term. What is that tangent xy over there? What? It's a product rule inside the chain rule, and it's implicit, which means Another chain rule, yes. So it is product rule within the chain rule while being implicit. When I saw it on the list over here, I just went, oh, where were you all this time? So let's go. Let's go. Ready? Find the derivative of this expression. So now tangent is the outer function. What is the derivative of tangent? Secant squared. So we start with the secant squared xy times the derivative of the inside. Now what's the derivative of x times y? It's a product rule, right? It's a function x times function y, so now we have to do the product rule. Copy the first, derivative of the second, plus copy the second times derivative of the first. Awesome. So now it's done. So finally we're done with the derivative of the tangent piece. Equal to derivative of x is? Plus derivative of y is? dy dx. We good? So what is the derivative? Well, we have to solve it for dy dx equals everything else. You just contributed to hatching the egg, right? One step, two steps closer. Now I'm wondering if at RVCC students, if RVCC students are going to start purposely parking on the parking lot 5 to hatch. Yes. By whatever you factored out. Yeah, we have to FOIL distribute first, right? Secant squared. And then move all the dy dx terms on the left side and all non-dy dx terms on the right side, and then go from there. So we have x secant squared xy dy dx plus y secant squared xy is equal to 1 plus dy dx. So x secant squared xy dy dx stays on the left, minus dy dx moved from the right is equal to 1 minus y secant squared xy moved to the right. Factor out dy dx, so that's the reason why you are grouping all of the dy dx terms on the left. So when you factor out, you get x secant squared xy minus 1 is equal to 1 minus y secant squared xy, and then divide to get dy dx alone. 1 minus y secant squared xy divided by x secant squared xy minus 1. And guess what? All of this is just the first step. Then find the tangent line. And when you're done with the tangent line, then analysis starts of whatever your application is. So next time when someone from algebra complains that they have a long problem, right? We just did a portion of the problem, I guess. Awesome. So meditate a little bit on this. Make sure you are understanding every aspect of the derivative. So this over here is the product rule embedded in tangent, which means the chain rule. And we have a y buried inside, which is implicit differentiation, which shows up there. So the derivative of tangent is secant squared of the same argument, multiplied by, as a chain rule, the derivative of this. Copy the first one. Derivative of the second one is 1 times dy dx, plus copy the second one times derivative of the first, which is 1. Equal to derivative of x is 1, derivative of y again is 1 times dy dx. At that point, you see that there is a dy dx buried in there. There's a dy dx on the other side. The only way to solve this is to put all dy dx terms on the left and then factor it out. Whatever is left out after factorization is the one that divides the right side, which is dy dx free, and then go on. Can we find the second derivative and the third derivative and the fourth derivative for implicit differentiation? The answer is hell yes, because you have the first derivative, go on, take the derivative again. Simplify it, take the derivative again. Now, one thing that you are supposed to notice now is that the derivative here contains both x's and y's, right? Where the previous lecture and lecture before that, when you find the derivative of explicit function, it only has x's. So that means that if you are to find the second derivative, you might have terms with dy dx only in there. And then, right? So that's it for today. Oh, what? Good. That's it for today. I'll see you all tomorrow. Same time, same place. Sorry I have to leave. We're going to do the rest tomorrow. And I'm just kidding.
And he just walks out and just is.
No, we're just going to do a second example now. It's all live on YouTube. What else? So, yes, as I was saying, so the second derivative might be in terms of x and y and the first derivative. So all of that could be mushed in the answer. Now, are we going to do second derivative here? Well, no. Because look, what do you have? You have a triple chain rule. You see them? Well, sorry, it's a double chain rule with a product rule inside. Secant squared with the xy there, which is the product rule. So that's a triple, and then that's also a product to this within a quotient. I mean, can it be done? Sure, but when do you do it? Sunday, 9 a.m. You have nothing else to do. Just crank it, make sure you turn the paper this way, and then you maybe just paste two papers next to each other like this, and start writing. 2 or 3 lines of that, you'll be done. Right? It's calculus. Cool. Use implicit differentiation to find 18 or 20. Flip the coin, 18 or 20? 18 it is. You approve? Or you're cheating, you're looking at the book. Go. Find the derivative in respect to x of this. So where do we start? Where do we begin? Nice. So derivative of y is 1 times dy dx. So we have dy dx is equal to, and now we have the quotient rule. So y minus 1 squared, y minus 1 times the derivative of the numerator is 1 minus x plus 1 times the derivative of the denominator, which is dy dx. And now we have to clean this up. So cross multiply y minus 1 squared to the left, because we can't have fractions all over the place if we are hoping to move things left and right using addition and subtraction. So we have y minus 1 minus, and do not distribute here because x plus 1 dy dx is already one term. Move it as a one term to the other side. So y minus 1 squared dy dx plus x plus 1 dy dx is equal to y minus 1. Factor out dy dx and get the y minus 1 squared plus x plus 1 equal to y minus 1, and just divide. And we're done. No bueno. Usually, believe it or not, the biggest stumbling block here is algebra. Everyone knows the derivative of sine is cosine and derivative of ln is 1 over x and so on, right? It's when it comes to algebra and shuffling terms around when we sense the disturbance in a force. So, looking at the expression here, we have the denominator that prevents us from moving the term x plus 1 dy dx to the left. That's why we cross multiply first and then move the term dy dx to the right, factor out dy dx. So it's always same steps. Another one? Yeah, why not, right? Let's do one of them because we can. It says find the second derivative. And they have problems 31 through 36. We still have an hour and 15 minutes, so let's do one. So what should we do? 32, 34, 36? All right. 32. 2x squared plus y squared is equal to 4. So you will first find the first derivative and then Let's see how it goes.
Are any of those second derivative problems? Oh wait, no, that's the chain rule.
No, this is a vanilla one.
Are any of the ones that have the chain rule?
No, the one has a product rule.
Okay, because that's what you were asking us earlier. That's a chain problem.
Yeah, it should take about 30, 40 minutes. It's not impossible. Guys, you have to understand the difference between hard and annoying. You know what's hard? Riemann hypothesis proving that that's hard. There's a $1 million price on it. All right. If you solve that, you get $1 million. That's the hardest way to earn $1 million. It's the hardest way. All right. To make $1 million. To solve that problem. People have been trying to solve that for 200 years now. All right. The planet collectively. Riemann hypothesis. So, yeah. This annoying. Not hard. Annoying. Riemann hypothesis is hard. I'm gonna check how to. Well, I'm officially disappointed. One student sitting alone took the test yesterday, the regular standard spin room, had a test on.
Over an hour early, right?
Yeah.
No, they're always, they start around 5, they work
Oh,
till
5?
7:30, yeah, that's when they usually go up. And they work in the room for about
All of them?
7 or 8, half.
So when they're there for 5 hours, the approximately 10.
10 people.
So they do math for 5 hours?
Sure, yeah.
They don't socialize at all.
They do. They all exchange the numbers, text each other, they do the Pokemon things.
You sure they're not just doing Pokemon instead of math?
I don't think
Well,
they
no,
do math
they're
for
just
5
walking around
hours.
with
I think they do a lot.
They are. They really are. Today they're taking probably a day off because yesterday they had a test. One student is working on the lab school right now. They're alone. I can guess that someone will show up next 10, 15 minutes. have on your part too.
Luckily, I don't have to do that.
I do. I'm still trying to pass it. I've been taking that every single semester. I took it summer one, I'm taking it again, I have it again in fall. Like I can't get out of that class. For years now, 5 years in a row. It's terrible.
I have to in the fall. I have to in the fall.
That's how it goes.
Yeah.
I do too. Make me not want to take.
I am the best instructor for it. That's I know it's like, yeah, I know, I'm doing my own work. Yeah, that's what I do. But I do certain things differently in that class, and it's not as much of a nightmare as in some cases. But I'm telling you now, if you don't know yourself, for this class, chapter 5, section 5, and if you don't know about 10 trig identities, please don't sign up. Quit now. If you're not going to learn those things, because no way you can do anything in that class without those things. And then you're going to Calc 3 afterwards. If you don't learn chapter 10 from Calc 2, just don't sign up for Calc 3 ever. That's how it goes. It is not standalone classes. They move from one to another, and I review a lot, but have no knowledge. My review is vague, and the class is not going to go well. That's how it goes. But I'm happy to announce that only 2 students failed the class in summer one. One student who had the average 30 across the board took the final, and one student who quit after the second exam did not go. Out of 24 in my class, and how to do it, all this stuff. Yeah, just could have withdrawn and got and taken like 50% money back. But no, just stopped showing up. And did not withdraw nothing, so there's that one transfer now. There's nothing I can do about it. I can put incomplete grade, hoping the students are going to show up sometimes to do something, but that reverse after 2-3 weeks on its own. No, pass the first test and the seventh maybe, and then start coming regularly to class. And that class is two days in a row. There's just so much material that you go through. And that's it. I am almost certain that the student would make it if he kept coming and doing work. Like any other class. The reason why how to is so notoriously evil and bad is because most of the integrals are using the technique that you learned literally last class of Calc 1 at RDCC. If you're not RDCC student and you didn't have that in your curriculum, and you take our Calc 2 class, you're screwed. The second thing is trig, going back a year at least, in education, and then the identities like the power reduction or double angle or some of those are not remembered and not used. You are again stuck and you can't perform, you don't remember Pythagorean identities for trig. You can't solve problems, you can't solve integral trig, substitution, all of those sections are gone. And then that's it. So that's kind of close. The first half, the second half is just sequences and series, which is a new type of mathematics you haven't seen yet at all. And it is extremely easy. I remember it as a student that being a living hell for me, like most everyone else is, because we have never seen stuff like that before. But now, when I actually figured out the right way to learn it, and now that I know it, I call it as the easiest part. And all of my students do the same thing. Hell on earth until you're done, and after the finals, like, right? So, yeah, that's how to have the reputation. But then, if you just listen and do things the right way, it's not going to be a problem. It's not going to be a problem. But there are students that are taking my time. We pound on it.
too fast. And I get a lot of students. My Calc 2 classes, summer 1, always packed. And everyone's Calc 2 summer class always packed because we take Calc 1 in the fall, and then a lot of students don't make Calc 2 in spring. And then they say, okay, we're going to do it over the summer. And then summer 1, first 6 weeks at RGCC, like people are sitting on top of each other. In Calc 2 classes, so we have a bunch of more than regular semesters. All the universities coming in. Thinking Calc 1, Calc 2, Calc RVCC easy. Just show up. That's it. It's community college.
We're supposed to take second derivative over here, right? We start the second derivative by figuring out the first derivative first. And that is going to be what? We have a supply underneath this. 4x, good, plus 2y dy dx is equal to 0. Very good. Now, (2y dy dx is equal to negative 4x, and then dy dx alone is negative 4x over this, so it's just negative 2x over y. That's the first derivative. And now we take derivative again. Now observe, when you add another d dx, the proper notation is d squared y over dx squared, because d times d is d squared y over dx times dx is dx squared. So just make sure that you have those squares on right spots. We're taking derivative of the other side, and it's a quotient rule, right? Wonderful. Y squared, negative 2, minus negative 2x, and then derivative of y is dy dx. And we don't have to do anything here, because we are looking for the second derivative, and as you can see, the second derivative is equal to everything else. I know that the first derivative shows up there, but guess what? This thing, which is the first derivative, actually plugs in there, right? If you want to simplify everything and have everything in terms of x and y. So negative 2y squared plus 2x, and then this is negative 2x over y divided by y squared.
The y squared in the numerator?
It's just y. It's clearly just y. Thank you. So now if you want to clear a little bit of algebra, as I said, that's the only thing you are algebra. We have negative 2y squared plus, no, minus 4x squared divided by y cubed. The reason why I multiplied y over y is I wanted to cancel the over y part in the numerator. So if I multiply numerator by y, I have to multiply denominator by y as well. So that would be the second derivative. And that takes care of that part. So we're going to see a lot more of these derivatives, and section 3.11, which is the section on related rates, is going to use these exclusively, and we're not going to have x and y as variables. Well, in some cases we will. Most of the time it's going to be t as the main variable, independent variable. So we'll stop stream now, and when we come back, 5 minutes or so, restart the stream with 3.9.